Hello everyone, this is Tita Bybee.
And Kevin Bell.
Our project goal is to model the cooling of thick soup.
We looked into the Idaho Food Safety and Sanitation Manual and found that bacteria growth occurs between 5 and 60 degrees Celsius. Food that remains in this temperature range for 4 hours or more must be discarded due to potential risks of bacterial growth. The focus of our project is to look at the time it takes to cool soups in a fridge.
The cooling of thin soup and thick soup will be different. For thin soup, free convection readily happens within the fluid. However, for thick soup, the high viscosity of the fluid might hinder free convection from fully occurring within the fluid. To simulate a stew and thicker soup, we chose glycerin. Corn syrup was considered as an alternative, however, we could not find the properties necessary. For glycerin, we were able to obtain a document full of properties of glycerin. And another reason we chose glycerin is because the viscosity of glycerin at 10 degrees Celsius is more than 100 times as big compared to the viscosity at 80 degrees Celsius. It was hoped that this big change in viscosity will be a good representation of thick soup.
In order to perform this experiment, we used an everyday normal fridge. We used a pot for cooking, which we put the glycerin in and we put it on a stove. The glycerin was then heated up past our desired beginning temperature of 80 degrees Celsius. Once it was heated up past that, we put cling wrap on top of the glycerin with 2 thermocouples underneath to prevent evaporation. The one thermocouple was placed in the center of the pot, measuring the middle temperature. The second thermocouple was placed on the edge of the pot to measure the change in temperature at that location. All of these were then placed on the oven mitt into the fridge, and a timer was used to measure the change in temperature every 10 degrees as it went down.
As you can see here, the center temperature and the edge temperature stayed the same with minimal differences. There was not any significant temperature gradient observed. The time it took to cool down were about the same for both the center and edge temperature.
Based on the experimental data, we then begun our calculations. In order to do this, we needed to find properties. The properties of air were found since it is the cooling fluid, and they were taken at 45 degrees C, or the film temperature between the fluid that was at 80 degrees C and the air at 10 degrees C. These were found in Appendix A4 from the Fundamental of Heat and Mass Transfer textbook. We also found the properties for glycerin. These properties were taken at 45.5 degrees C, and this temperature was determined as the average because the initial temperature was 80 degrees C and the final temperature was 11 degrees C. These properties were found from an article titled Physical Properties of Glycerin and Its Solutions, and a link to that article is included on this screen.
So then calculations could be done after we found the properties. The diameter of the fluid was 139 millimeters while the depth was 10 millimeters. Because the depth of the fluid were small compared to the diameter, Nusselt correlation for flat plate was used in order to calculate the heat transfer coefficient. It was calculated that the heat transfer coefficient to the air in the fridge at 10 degrees Celsius was 7.70 watts per meter Kelvin, which is within the acceptable range for heat transfer coefficient of gas in free convection.
Using that calculated heat transfer coefficient, we then looked at the lumped capacitance method and determined that it was a valid method for determining the elapse of time. In order to check this assumption, we looked at the BO number and found that it was significantly less than 0.1. This allowed us to use the lumped capacitance and find the time that it took, the theoretical time that it took to cool the soup.
As can be seen in the graph, the actual time for glycerin to cool down from 80 degrees Celsius to 11 degrees Celsius was about 4,700 seconds. However, when we did the calculation using the lumped capacitance method, the expected time elapsed, T, was found to be over 6,800 seconds. So we had to think of what could be the reason these times were so different. And it is perhaps because of heat losses that weren't taken into account. For example, the insulation on the bottom of the pot may not be thick enough and actually allowed heat transfer from the bottom of the pot. It could also be from evaporation that took place while getting the pot ready to be put inside the fridge, which may have caused the actual volume to be smaller than when it was measured before heating.
The end result is that the anticipated change in the heat transfer of glycerin did not reflect that of a thick soup. There was not a significant temperature gradient observed as expected or hoped.
Thank you for watching!